In this video, I'm going to talk about the absolute value family. So the first thing that I wanted you to do was I wanted you to graph the parent function for the absolute value family, which is the most basic function of the type. So it just means I have the absolute value of x, and then I might have extra stuff. Just has to have the x inside of absolute value bars. So if I were to plot this on Desmos, I would have seen that I had a vertex at 0, 0, and then if I plugged in 1 for x, I would get out 1, and if I plugged in 2 for x, I would get out 2, and if I plugged in 3, I'd get 3, 4, 4, 5, 5. And then on the other side of 0, if I plugged in -1, the absolute value of -1 is +1. The absolute value of -2 is +2. -3, +3. -4, +4, etc. And then I'm going to connect these, and I want it to be black. And then I'm going to connect these in a V shape, and it's going to look like this. Where is the lowest point located? It's the vertex, which is at 0, 0. This is the lowest point, and I call that my vertex. And then what values of x could the function use? That's asking me for the domain. And the domain in this case is, I'm going all the way to the left. This thing keeps going on and on and on. So the lowest x value will be -infinity. And then I'm going on and on and on to the right. So the highest x value would be +infinity. But I just write infinity. So I'm starting with my lowest value, which is -infinity. I'm putting comma, +infinity. I'm putting parentheses on both of them because you cannot contain infinity, and parentheses means not included. All right, then I am asked for my range, which is all the included y values. And those, if I look at my lowest y is a 0. And then my highest y, if this thing keeps going on and on forever, is infinity. So I'm going to write that my range is 0 to infinity. Now I put a parentheses on infinity always, but on 0, this point is shaded. So I am going to put a bracket on it because that y value is included on the graph since it's shaded. Then I am going to graph this parent function again, the one I just did, y equals the absolute value of x, and I'm going to put this on the graph. So I already graphed this. I know that it has a slope of 1 to the right-hand side, and then there's an axis of symmetry, just like the parabola that we looked at before, and I can reflect all of those points on the right over this line here, which is the axis of symmetry. I'll talk about that more in the notes. So this is my parent function. That's the parent. And then I'm going to graph y equals 3 times the absolute value of x. If I graph that thing, if I plug in 0 to start, I'm going to get 0 out, so I'm going to have the same vertex. If I plug in 1, I'm going to get 3, so I'm going to plot that. And if I plug in 2, I'm going to get 6, but that can't fit on my graph. If I plug in -1, I'm going to get 3 times the absolute value of -1, which is 3 times 1, or 3. And I'm going to see I have a V shape, and I want to see what is the change between the one in gray and the one in blue. So what's the change? I would say that the change from the parent is that it's steeper. So it's kind of like 2 lines connected, and each line's slope, this slope is 1/1, and then this slope would be 3/1. So it has a steeper slope, and it looks steeper. What we call this in math is a vertical stretch. So we are basically taking the graph, taking the V shape, and we're pulling it up and down, and that makes it skinnier or steeper. So we're pulling it like this. It's a vertical stretch. The next thing that I wanted to graph was y equals 1/3 times the absolute value of x. Now I want to plug in x values that are divisible by 3, because multiplying by 1/3 is the same as dividing by 3. So if I plug in 0, I'm going to get 0. If I plug in to the right of that, I would pick 3 is the first number to the right of that that's divisible by 3. So if I plug in 3, I'm going to get 1/3 times 3, which is 1. And then on the left, if I plug in -3, because that's the first one on the left that I can plug in, I'm going to get same thing, +1. And the next number I could plug in is 6 or -6, but those aren't going to fit on my graph, so I'm just going to draw these like this. Plus, I only need 2 points, really, when I know this is going to be a line on either side to form a V shape. So this is what I'm going to have. Boop and boop. All right, how did the function change from the original? So now I'm going from the gray to the purple, and what I'm seeing is that it's less steep. So this slope of this line is flatter than the slope of this line here. So I would say it is less steep. And what we say in math when we see that change, we call it a vertical, instead of stretch, we call it a vertical shrink. And what that means, or what we're doing, is we're compressing the graph vertically. So it's like we're pushing that V shape. We're squishing it to be flatter. What effect does A have on the graph? So A is that coefficient. It's the coefficient. When I saw 3, it got steeper. When I saw 1/3, it got less steep. So what is going to happen is A has an effect. It changes the slope. And then I want to know, for what values of A does the graph get steeper? And then for what values does it get less steep? So when I saw that I had a whole number, it was different than when I saw that I had a fraction. And that's the distinction that I have that's going to change if it's going to get steeper or not. So I'm going to say if the absolute value is greater than 1, then that means it gets steeper. And if I have the absolute value of A is less than 1, meaning that it's a fraction, then I would say it's less steep. So that's that. And then let's do the next problem. If I have, first I'm going to plot the parent function. So I'll do 0, 0, 1, 1, negative 1, 1. I'm just going to connect those because I know that's what it looks like. Oopsies. I don't need to be perfect. These are kind of just sketches for right now. Although I can be perfect because I have an iPad. And here we go. Like that. That's my parent. Make sure you're drawing the arrows on the ends and indicating it goes on and on forever. Then I'm going to, the second one I'm going to graph is y equals the absolute value of 2x. And the way this differs from the previous example is that the 2 is inside instead of on the outside. And I want to see how is that going to affect the parent function if I have the coefficient inside. Well, if I plug in x is equal to 0, I'm going to get 0. If I plug in x is 1, I'm going to get 2. If I plug in x is 2, I'm going to get 4, and 3 won't fit on the graph. Then I'm going to go to the other side. If I plug in -1, I'm going to get 2. If I plug in -2, I'm going to get 4. And I'm going to connect these, and then what I'm going to see is that, the function got more steep again. So if it had the whole number coefficient on the outside or the inside, I saw that it's steeper. The only difference is that when a number is on the outside, I talk about it as what's happening vertically, like what's going to happen to the y. And when it's inside, I'm talking about what's happening horizontally. So it's steeper. What's happening horizontally is it's going to be a horizontal shrink. So that means that I'm compressing it horizontally, which means I took this function, I pushed it in, and then it became this function. I pushed it in from the left and the right, and it became the blue function. So we call this a horizontal shrink. It's the same thing as a vertical stretch because they're opposites of each other, vertical and horizontal. The next one that I'm going to graph is y equals 1/2 x. If I graph that, I'm going to plug in x is 0, so I put that there. If x is 0, then y is 0. And then if I plug in values for x, I want to pick ones that are divisible by 2 because multiplying by 1/2 is the same as dividing by 2, and I want whole number answers. So the next one I would pick is 2. If I plug in 2, I'm going to get 1. The next one I would pick is 4. If I plug in 4, I'm going to get 2. And then on the other side, I can reflect those points there and there. And then I'm going to connect them. And I'm going to see that once again, if I had a fraction as a coefficient, inside or outside, the graph gets less steep. So it's less steep. That's what I'm seeing, and what that's called in math is, and if it's in the inside, we talk about what's happening horizontally. It's a horizontal stretch, which means that I am going to be pulling the left and right outwards. And so I go from here to here. When I do that, it gets wider and flatter. Okay. You can think about it how you want to. If you want to think about it as a vertical stretch, then it's the same thing as a horizontal shrink. And if you want to think about it as a vertical shrink, it's the same thing as a horizontal stretch. They're the same thing. What effect does b have on the graph if I have b as the coefficient of x inside of the function? Well, again, it changes the slope, just like it did if there was a coefficient on the outside, it changed the slope. And then it asks for what values of b does the graph get steeper? Well, if that's for b values that are greater than 1, it gets steeper. And then for values of the absolute value of, when the absolute value of b is less than 1, then I know it's less steep. And this is when I have refraction. And the other case is when I have, it doesn't have to be a whole number, it could be any number really. Okay, and that's the warm-up.